So now that what we're going to be looking at are going to be optimization problems, and optimization is basically when you are determining points that either create a maximum or minimum. So we're basically looking at points of extrema, right? And this can be a variety of different scenarios. For instance, if we're looking at a cost function, we want to look at a point that minimizes cost in a business point of view. If I'm producing X number of goods, right? Or if we're looking at a revenue function, we want to maximize revenue because we want to maximize return as much as possible. Or if we're looking at creating area or volume, constructing it with certain dimensions, we want to maximize area and volume respectively, right? So optimization is it's really the strive to kind of maximize or optimize certain conditions, right? And we can actually do this if we are given a function. We can actually optimize or determine the maximum minimum point by using the first derivative test, right? We know that at the first derivative, if f of x contains a derivative f prime of x, then when f prime of c is equal to 0 and extrema occurs at c and f of c. Okay? So this extrema could be a maximum or minimum point. We know that a maximum point is a concave down portion. This point here has a slope of 0, and a minimum point, concave up portion, at this critical point here, there is also a slope of 0. Okay, so either or case, right? We could basically determine the extrema to find the value that is either a maximum or minimum. So that's how we optimize the scenario, right? Let's take a look at this scenario here. The height h of a ball t seconds after being thrown into the air is given by the function h of t is equal to negative 4.9 t squared plus 19.6 t plus 2. Find the maximum height of the ball. So this is an example of projectile motion, right? And if we want to figure out the maximum height of the ball, we know that the maximum height will occur when h prime of t is equal to 0. Now, in previous portions of the section, we looked at the relationship between position and velocity acceleration, right? The kinematic functions. We know that h prime of t is a velocity function, v of t, right? But for our discussion per se, we can just kind of address when is the maximum height occurring. So we're just going to look at this separately. Okay. So in this case, let's find h prime of t. So h prime of t here is the derivative with respect to t of negative 4.9 t squared plus 19.6 t plus 2. Okay, just gonna clean that up a little bit. Okay, so 19.6 t plus 2. And in this case, the derivative is negative 9.8 t plus 19.6. Okay, so this is our first derivative, right? And we know that an extrema occurs when h prime of t is equal to 0. Okay, so we're going to let h prime of t equal to 0. We get negative 9.8 t plus 19.6 is equal to 0. And we want to solve for t because we want to figure out the time when the maximum occurs. So negative 9.8 t is equal to negative 19.6. And then if you want to solve for negative 9.8, if you want to solve for t, you got to divide by negative 9.8. Right, so this cancels out, and then t is equal to 19.6 divided by 9.8, right? So if I punch this out, I get 2, okay? So this is 2 seconds. So in 2 seconds, you actually should get to the maximum height. Well, what is the maximum height? Well, we know that at 2 seconds, the height should be h of 2, right? So h of 2 should be our maximum height. So h of 2 here, if you plug into your original function, you get negative 4.9 2 squared plus 19.6 times 2 plus 2. H of 2 here, if I plug this in, I crunch this out. This is going to give me 21.6 meters, okay? So therefore, the maximum height of the ball is 21.6 meters. So this is why calculus is so useful, because we can optimize our scenario and figure out the maximum minimum points by using the first derivative test.